Okay. Good afternoon, good morning, good evening. So I'm going to do a couple more proofs from section 1.8. Um, and yeah, so that's it. So let's start this. So our first example, if I can find what to share. Where are we? Hello, this. Yes, thank you. Okay, so our first example for today is a game called Chomp, which you may have heard about or not at all. It makes no difference. So here's the setup. Okay, so there are two players, and there is a board which is rectangular. I'm going to show you a picture in just a sec. Okay, can be any size. Okay, we'll discuss this in just a sec. Right, and so it's this rectangular board. It's like a chessboard. It's divided into squares, and the squares contain cookies like this. Okay, and there is one bad cookie here full of poison. So each square contains a cookie. That's hard to read. Let me try that again. Each square contains a cookie. Top left cookie is poisoned. So you don't want to eat that one, obviously. Okay. Now, what's the game? So the game is this. So at each turn, so players play one after another. A turn consists of this. So player selects a square, right, and must eat all cookies below or right of that square, including that square. Okay, so at each step, each player must select a square and eat all the cookies from that square, bottom and right. So let me show you, let's say, what one possible move could be. So let's say the player selects this square, then the player must eat all the cookies over here, right? And then the second player must at that moment select a new square, and we keep on going like that. Okay, so let me show you an example of this an instance of the game. So here's, I just stole that from Wikipedia. So they made it look like a chocolate bar, which is kind of cool. So on the left here, you see the original rectangle, and the top left, as you can see, is poisoned. So now player one selected the rectangle here, the square here, sorry, and so player one has to eat everything below and to the right. Then player two chose this square, so everything below and to the right means those cookies or squares. And then player one again chose the top, not the bad one, but just this one here, and so had to eat everything below and to the right. And then finally player two selected this, ate everything below, and look what happens. Player one has to eat the poison square and loses, right? So that's how this game ends. So let's go back here. Yes, okay. So player who is forced to eat the poisoned cookie loses, obviously. Okay, so that's the game. So what's the question? The question is this: we're asked to prove that player one has a winning strategy. And so I have to tell you what a winning strategy is. And if you're really, really smart and inquisitive, and you're looking at this, you'll say this is false. We'll never be able to prove that, because if the rectangle is only 1 by 1, player one will certainly lose, because player one has to start and will have to eat the cookie. So we have to add if the rectangle is larger than 1 by 1. So if there's only one square, player one will lose, but that's not a very interesting game. Okay, so what is a winning strategy? So what is that? Let's define this. So let's go to the next page. So a winning strategy. We're not going to go into this in a lot of detail, but this is like there's a lot of stuff there. You can search by yourselves on Google and read books, and you'll see on combinatorial game theory, there's a lot of stuff out there, and it's very interesting. So I'll keep this as simple as possible. So here, a winning strategy is an algorithm that tells the player which move to make depending on previous moves, right, by both players, right? So it's an algorithm that tells the player what to move depending on what's happening up to that point in the game, that that guarantees, that guarantees player wins. Okay, so again, there are slight variants in some games where if a tie is possible, so then a winning strategy would be considered something like you can't lose. But in this particular game, and this is the first remark I'm going to make, one player has to win and one player has to lose. A tie is not possible. Okay, so the first remark, the first observation here, so player one or two will win always, because as you can see at each step, at least one cookie has to be eaten. So the number of cookies is reducing every time. So eventually some player will have to eat that last cookie because the number of cookies decreases strictly at each round, right? So you can't stay at the same place. So this will eventually force one player to eat that last poison cookie and lose. Okay, so this is forced. So there's always a win. Okay, now it's not clear that it doesn't mean that there is a winning strategy for either player, right? That's not necessarily obvious. But we're going to prove that actually there is a winning strategy for player one. And it's a very sort of silly argument, okay? which is the following. Okay, so player one does have a winning strategy. And here's the proof. And we discussed this last time. It's a non-constructive proof in the sense that I'm not going to tell you what the strategy is. In fact, as far as I know, nobody knows an actual winning strategy for Chomp. For all, there are some obvious special cases. If the rectangle is 1 by n or n by 1, it is clear, it's trivial. I think maybe for square rectangles, there might be a winning strategy that's easy, but a general winning strategy for any size of board, I don't think that's known. So this is a non-constructive proof in the sense that we will not actually see the winning strategy. So we're just going to show that it exists, right? Okay, good. So here's the argument. Okay, so I have a rectangle like this, and consider the following move by player one. Just choosing the bottom right cookie. Okay, so consider the following first move by player one. So take bottom right cookie. Okay. There are two possibilities. So case one, this is actually so if there is a winning strategy for player one, okay, then there is a first move, right? So this first move of the strategy tells you, well, do this, and then player two will do something, then you respond. If player two plays this, then you do that, blah, 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 and so on and so forth. So there's a first move, okay? So if that move here is the first move of a winning strategy for player one, obviously we're done, right? So if this move is the first move of a winning strategy, it means there is one of a winning strategy for player one. We are done. There's nothing to prove, right? I'm making the hypothesis that what I want to find exists. So that's it. So I have to consider the second case, right? So second case is it is not. So what does that mean? It is not the first move of a winning strategy. So that means that player two can respond with some move such that player one will never be able to win after that. All right. So this means this. This means this. Means player two has some move after which player one can never win. Right? Well, think about it just a few seconds. So what is this move? This move is selecting some square somewhere, let's say here, right? Or it could be here, but at any rate, it will cover that bottom right square, right? Any move by player two. So that's an important observation. So let me copy this here. And let's move here. Okay. So any such move will contain the bottom right cookie, right? It's clear. Wherever you put that next square, you'll have to, the rectangle will contain. So what does player one do? If player one starts with that actual move, then player two can never respond in a way to win after that. That's exactly what we're saying here. Okay, so if player one starts with that move, player two has no response to win, right? So you're flipping basically the two players in that sense, right? So if that first little move from player one is the first move in a winning strategy for player one, we're done. Otherwise, it means player two has a response that will prevent player one from winning from that point on. So that means that if player one starts with that actual move, the red move I put here, then player two is forced to respond as player one would have been in the previous hypothesis. So then player two can never actually win after that. There must be a way for player one to respond every time to win. So that means that's the first move of a winning strategy. Hence, that move is the first move in a winning strategy for player one. And that's the proof. Perhaps not a very satisfying proof because it doesn't tell you actually how player one can always win, right? But by the way, the argument for tic-tac-toe is essentially the same. It's actually a bit more subtle for tic-tac-toe, but there is a winning strategy if you know that game. For player one in tic-tac-toe, winning in the sense that non-losing, because a draw is possible in tic-tac-toe. So that's the proof that player one has a winning strategy, but we're not actually providing it. Okay, let me show you a similar example. Similar in the sense that it's a game again. So this is, again, a two-player game. This is a classic. This is a special case of a very classic game. We have a pile of 15 stones. Okay, there are two players. So what's a turn? So a turn by one player. The player can remove 1, 2, or 3 stones. Okay. And what is a win or a lose? The win is you remove the last stone. So it's the opposite of the chomp game, right? So if you manage to take the last one out, you win. So remove the last stone. Okay, so that's the game. So there are 15 stones. Player one starts by removing 1, 2, or 3 stones. Then player two responds by removing 1, 2, or 3 stones, and they alternate like this. And the game, the idea is for each player to try to manage to get the last stone. Okay. So again, we have to show that player one has a winning strategy. Okay. Now, this time, if you look at this and you, so the idea basically, if you're asked to do a problem like this, okay, you think about it, you play a little bit with the game, and eventually you'll probably figure out, okay, here's what here's the idea, here's how we do it, okay? And that's what we're going to do. I'm just going to mess around a little bit with the game. You're going to see how this works. And once you see it, then we just have to write it up. Now, for that kind of problem, obviously you have to explain in words what you're saying. That's the argument, right? As opposed to the previous example, this one, we're actually going to describe the strategy, okay? So let's take it from the last step, okay? So what does player one want, right? So let's reverse engineer the whole thing. Okay. So player one wants to remove the last stone, right? So player one wants to remove the last stone. In other words, so how can player one be sure to remove the last stone? Since a move means removing 1, 2, or 3 stones, it means player one wants to see on the board 1, 2, or 3 stones, right? So player one wants to see 1, 2, or 3 stones left. Clearly, right? So if player one sees 1, 2, or 3 stones on the board, then player one can remove the required number of stones and win. Okay? So how do you guarantee, how can player one make sure that there are 1, 2, or 3 stones left? Now, if you think just a little bit about it, so the previous move, player two had to remove 1, 2, or 3 stones and leave 1, 2, or 3 stones. Now, if you think about it, here's the key point, the key trick. So if player two had 4 stones on the board, player one is good. Right? Because if there are 4 stones and player two has to remove 1, 2, or 3, what will be left? 1, 2, or 3, right? So player two is forced to leave 1, 2, or 3 stones. Okay? So now it means that if player one can force 4 stones on the board, player one will win. So how can player one force that, right? Player one will remove 1, 2, or 3 stones. So in other words, player one wants to see, well, oops, 4 plus 1 or 4 plus 2, 4 plus 3 stones, right? By removing 1, 2, or 3 in that at that moment, that will leave 4, and we know after that it works, okay? But you see, it's exactly the same, it's the same thing. How can player one make sure that she sees 4 plus 1, 4 plus 2, 4 plus 3? If there are 8 stones on the board, then player two will be forced to leave that like that. So in other words, if player two sees 8 stones on the board, right? And now you see the pattern, right? So if player two is stuck with 8, he or she will have to leave 4 plus 1, 4 plus 2, 4 plus 3. Then player one can remove the required number to leave 4 to player two, and so on. So 12 is the right thing now, okay? So same reasoning. If player 2 sees 12 stones, player 1 is happy. Okay. And so we started, let me go back up. We started with 15 stones. So can player 1 force 12? Yes. Remove 3 and that's it. Okay. So if player 1 removes 3 stones from 15, leaves 12 stones for player 2, right? And then player 2 will play and player 1 will play to leave. So after player 2 plays, player 1 plays to leave 8 stones. Then in the same way, plays to leave 4 stones. And then after, man, that's long, eh? After player 2 plays, we'll remove the last stone. Okay, so what is the strategy in general if you don't start with 15, but with another number? If you start, you can see that multiples of 4 are the key, right? So the algorithm, the winning strategy is leave a multiple of 4 number of stones to your opponent, right? So if you do that, you're good. And because you're starting with 15 and not 16, then player 1 will win. If we started with 16, then player 1 would be in trouble, right? So it would flip the whole thing, and player 2 would have a winning strategy. Okay. This is not the most formal proof, obviously. This is sort of an explanation of why it works. And because we started with 15, it's simple. If we wanted to prove this properly, it would be a little trickier, but let's leave it at that for now. Let's just keep it like this and that'll be fine. Okay. Here's a cute one, which is also similar. I mean, this section of the book is entitled Proof Strategies. And so it's taking stuff from all over the place. But I mean, the strategy here is just you have to think about it and figure it out. That's the strategy. So this is a problem involving tilings of a chessboard. Okay, so we have an 8x8 chessboard. It's a chessboard, so it's 8x8, but so it's a square which is divided in little squares, and it's 8x8. Okay, so that's the chessboard. Okay, and we also have dominoes. What's a domino? It's a 2x1 rectangle, and I mean, obviously, you know, could be either way. And we're going to place those dominoes on the squares of the chessboard. Okay, so a tiling of the board. You place the dominoes to cover, so on the board, covering 2 squares, obviously, with no free squares. It's a tiling, so it means you have to cover everything and then no overlaps. You're not allowed to have dominoes on top of one another, right? So the first question is, so question 1, does there exist a tiling of the 8x8 chessboard? That's an easy question. So you might think about it a little bit just to make sure you're not messing it up. But yeah, of course there is, right? So here's so there are tons of them, right? So I'll just put little, you can just do it like that, right? I mean, there are tons of ways of doing it, but, and so on, blah, 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 right? Yes. There are tons of them. Okay, so that was our first question, was really easy. Second question. Right, by the way, notice it's an existential question, so the proof is yes, there you go, boom, that's one, that's over, right? Question 2, let's say we remove the top right corner of the chessboard. Now, does there exist a tiling of the truncated board? Right, so we're looking at, let's go here. So that's my second question. So I have the board now looks like this. I hope this works. Ugh, okay, whatever. Okay, whatever. Sorry. So this is the new board, right? We've removed the square and we ask, is there a tiling of this? And all of you will go, well, no, right? And the answer is no, because, and it's easy. So answer no, because if we have a tiling, of course, we need, for each domino, we need 2 squares. And now we have an odd number of squares, so it's not going to work, right? So now we have an odd number of squares, and dominoes cover 2 squares. So a tiling implies an even number of squares, right? Nice and easy. Okay. And now here's our third question. And many years ago, one of my colleagues in the humanities department invited me to give a talk in one of his courses for non-math students. So I wanted to find the cutest, simplest possible mathematical proof that I could actually show them, that they could understand and get a feel for what a mathematical proof is without it being complicated. And it's the next one. That's what I found. I thought that was the best. So here's our third question. We remove top right corner like we did, and bottom left corner. Now, is there a tiling? So this is what this looks like. And you'll see why I'm doing that like that. I have to outsmart the technology. I don't know if I'm. Maybe. Okay. Okay, so this is what this thing looks like. Okay, so the question is there a tiling of this board? Now, the argument of the parity doesn't work anymore, right? So we do have an even number of squares. So you can try. And I remember last year, that's one of the last live classes I ever gave. Live in the sense of being in the same room as students. So we messed around and students were doing, okay, well, we can try this and this and that. And it never worked. There was always a bug. But the thing is, why does it always fail? Is there a simple argument why it fails? Because it always fails. The answer is no. And the question is, why? So how can you how can you convince somebody that there is no way? I mean, you can try. I mean, there's a lot of possibilities, right? You can start placing dominoes and this and that. But there's actually a very simple argument to show that this doesn't work. So here's a simple, and I drew my chessboards in a specific way just for that reason. So now, I mean, to save time, obviously, but here's the argument. Now, usual chessboards don't look quite like this, right? They do actually have colors on the squares. So let's color a few of those. So this might be like that, right? Now you'll say, what could that possibly do to help? Okay, anyway. So this, right? It alternates. Sorry, this is really boring. Okay. All right. So that's what the actual chessboard really looks like. And that's a pretty good hint. So what's the answer? So if you put a domino and you're going to cover squares 1 by 2, 2 by 1 on the, you're always going to cover a white square and a black square. That's forced, right? So notice a domino must cover one white square and one black square. Always, wherever you put it, you're always going to cover one white and one black all the time. So if you have a tiling, it means that you must have covered the same number of white and black squares. So a tiling must cover the same number of black and white squares. But look, the squares were removed. Both are black squares. But both squares we removed or black, same color. So it's not going to work, right? Because if I start placing dominoes, black, white, black, white, black, white, black, white, I'm going to run out of black squares, right? So no tiling is possible. That's the proof. Which is cool. Hopefully you found that cool. Okay, so that's the argument. That's the simplest argument. So there is no tiling. Now you can try for various different kinds of possibilities, removing pieces of the chessboard and all that, and becomes a bit more complicated. That's another story. Okay. What time is it? 11:30. Well, I'm not supposed to tell you the time, right? This is a in limbo time. How long have we been doing this? I don't know. I don't know how long. Okay. That'll be it for this. That's it. That's it for this little video. So I guess if you're watching this before class, I'll see you in just a few minutes. Otherwise, we've seen each other already. Okay, that's it. Cheers.